Hi, my name is Merryn, and I'm an assistant professor of science education at the University of Nevada, Las Vegas. Today, I'll be sharing some background on spatial thinking, including what it is and why it's important, and then providing an overview of a couple of recent studies that incorporated spatial thinking in astronomy education. So first, what is spatial thinking? Spatial thinking is the perceptual and cognitive processes that enable humans to create and manipulate mental representations of the spatial properties of objects, structures, and systems. It also includes the capacity to use external representations or internal representations, like mental models, to make inferences or solve problems about the spatial properties of these same things. It's important to point out that it's not just about making a representation, but it's also about using these representations in order to address issues, solve problems, and understand what's going on. So what does this look like in STEM fields? Well, in chemistry, we spend a lot of time representing molecules. Molecules are too small for us to easily see or manipulate at the particulate level. So instead, we make these representations. All of the ones on the left are the exact same model, but which representation we use will depend on what our purpose is. In blue are representations from mathematics, where you might have an object and you need to think about or represent what it looks like if it's been rotated or translated in some way, or perhaps if we had to take a cross section or look at it from a different perspective. Then there's an example from geoscience where we may have to consider how different landforms were formed when we can't physically go through and necessarily cut through them to see it, at least not on a scale where it makes sense at the landform level. In biology, sometimes there's things where we can directly investigate, but sometimes it's either inconvenient to cut something open, or it might just be something too small like DNA, and instead we have to use models and representations to investigate these things instead. Finally, here's an example from engineering where we regularly need to make two-dimensional or three-dimensional representations and often go between the two, and also understand how they not only relate to each other, but how they relate to objects in the real world as well. What might this look like in astronomy? Well, one of the things I do in astronomy is investigate people's understanding of moon phases. Often moon phases are taught as not much more than a vocabulary lesson where there might be a series of photos that show the order the phases progress through, and we talk about what each is called. But when we want to teach about the cause of moon phases, we need to go beyond that and use that to explain perhaps why the moon might look like one or more of these images at any given time. Only one of these is an eclipse, but if you don't understand things like the scale of the system or that the system is constantly in motion, you won't understand why the phases can't be caused by an eclipse or another shadow, or perhaps something blocking part of the moon from our view. So one of the challenges, the scale is too big for us to physically manipulate. So instead we have to make a model, whether it's an internal mental model or if it's an external physical representation of it. And then since the objects within the model are constantly in motion, we need to use a lot of mental rotation skills and consider the dynamic aspects of the model instead of just the physical representation of these bodies. So why is spatial thinking important? Well, it's correlated with understanding of STEM content, including astronomy. It's also predictive of both participation in STEM and also of earning higher level achievements, such as earning a PhD versus a bachelor's degree. It's also really important for novices as they tend to use decontextualized spatial thinking in order to address problems, as opposed to using memorized algorithms or other content knowledge as experts would. So the first study I want to highlight is where we used a hierarchical linear model to explore the use of a project-based unit to teach lunar phases. We asked 4 research questions. So after instruction, did a student with higher lunar phases understanding also tend to have a higher spatial assessment score? Similarly, did the increase in understanding of moon phases correlate with an increase in their spatial thinking ability? Was the unit effective in improving student understanding of moon phases? And finally, among a variety of measures of student demographic characteristics and contextual factors from the teachers, which ones significantly predict their content knowledge of lunar phases? So we gave both teachers and students 2 assessments prior to and after instruction. First was the Lunar Phases Concept Inventory, which is a 20-question multiple choice test that measures understanding of moon phases. We also gave the Purdue Spatial Visualization Test for Rotations, which is also a 20-question multiple choice test, but this one measures mental rotation specifically. Mental rotation is one type of spatial thinking ability that is highly relevant to astronomy, especially things like moon phases. So the Purdue assessment shows a block and then shows that same block rotated in some way and asks if this different block was rotated in the same way, what would it look like? We also provided professional development to the teachers before they implemented the unit in their classroom. That professional development covered content understanding to make sure they understood the cause of moon phases and related ideas. It also explained why and how the lessons were designed the way they were, because sometimes teachers will adapt the lessons to their classroom, which we think is great, but we want to make sure that they understand how and why the lessons were designed the way they were so that teachers don't inadvertently take something out that's really important when they adapt those lessons. We also provided classroom materials to the teachers to make sure that they had everything they needed to implement these lessons. So since this research is partly related to the use of project-based units, I want to take a minute to mention project-based instruction. One of the big misconceptions is that you teach something and then you do a project. And that's not really what project-based instruction means. Instead, the project should really be driving the unit. So each project-based unit will have a driving question, which provides a broad umbrella for the topic of the unit. In this case, it's why does the moon's appearance seem to change every day? And then students create sub-driving questions related to that driving question in order to guide their own project work. Also, the project should be introduced early enough in the unit that it really is driving the instruction. So while teachers will use benchmark lessons to scaffold understanding and make sure that they're addressing the standards, they may also add benchmark lessons as just-in-time lessons to address content or skills that come up within project work that students need to learn along the way. This is a summary of the units in REAL. REAL is short for Realistic Explorations in Astronomical Learning. If you want to learn more, this has been published in a book in 2019. The entire unit is there if you'd like to see it. A couple of things I wanted to highlight quickly in this unit. One, we use moon journals, which are kept for usually 4 to 5 weeks, so students can start to see the cycle of the phases repeating. They not only record the appearance of the moon, but they also write about what they're seeing. Some of this writing could be looking for patterns, it could be trying to make sense of what they're seeing, or it could be things that they're wondering about as they make observations. Another lesson is related to the scale of the Earth, Moon, Sun system, because we know that if the scale of the system is not understood, it's easy to think that an object blocking part of the moon or a shadow or things like eclipses are actually causing the moon phases. Finally, the last lesson is Moon Finale, where students use foam balls and a light to investigate the Earth, Moon, Sun geometries necessary to produce the phases of the moon. One of the things that makes this lesson a little bit different from similar modeling lessons is that we don't just ask students to place the foam balls in locations to represent the different phases. We ask them to figure it out for themselves a bit, including referring back to their moon journals. So for instance, we might ask them to model a waxing crescent moon. As part of that modeling, a lot of students will set it up and make a shadow using their using their Earth to make a shadow on the moon. Well, then we tell them to look at their moon journal and find where and when they observed a waxing crescent moon. And they'll figure out that they saw it in the southwestern sky in the early evening. They look at their model and realize that it's not in the southwestern sky and it's not the right time of day. When they take that model and then move it to match what they saw in their moon journals, they're not only self-correcting and using those models to learn, but they're also making a connection between their classroom modeling and what they observed in the real world. So for the first 2 questions, we indeed found that students' lunar score was correlated with their spatial score, and also their increase in understanding of moon phases was also associated with increase in spatial thinking ability. This is not surprising, as we've seen this in previous research. Then we ran a hierarchical linear model in order to investigate other factors that impact students' lunar phases understanding. As we added predictors to the model fit criteria decreased with each model until we hit model 4 and found that that one had the optimal fit. So model 4 shows that the unit was effective in increasing student understanding of lunar phases. It predicted that on average, students would increase their scores by 14.8 points from pre to post instruction. This again was not a surprise, as previous research has shown that this unit is effective in improving both students' understanding of moon phases as well as increasing their spatial thinking ability. As far as significant predictors, we were surprised to find that gender was not significant. As in previous research, we have seen differences between genders. In the literature, typically boys are better than girls at spatial thinking, although a caveat is that boys tend to be more varied in scores than girls, meaning that the high spatial boys tend to be higher than the high spatial girls, and the low spatial boys tend to score lower than the low spatial girls. And we also found no significant difference by gender in our data. Students from 2 race ethnicity groups, Hispanic American and other, and all of the race ethnicity groups were self-reported data. These 2 groups performed significantly worse than their white classmates. We don't have a concrete, definite explanation for this finding, although we wonder it could be related to things like language. For instance, if some of the Hispanic American students were English language learners, then it would make sense that they may struggle with instruction or the assessments. Student spatial score was a highly significant predictor of moon phase understanding, which again is not at all surprising given that we know that the 2 are correlated. Finally, the most interesting thing to us was the teacher GSV score provided highly significant explanatory power of student lunar phases performance. So what does this mean? First of all, GSV is one of the 4 spatial domains that we can categorize the LPCI questions into. It's geometric spatial visualization, which refers to considering a system from above, below, or within the plane. So second, thinking about this as a teacher characteristic impacting student learning makes a lot of sense. While teachers can't teach content they don't know or don't understand, similarly, it makes sense that if teachers haven't developed their own spatial thinking ability or understands its importance, it would be difficult or impossible for them to foster spatial thinking development in their students. So this is an example of what it may look like. This is a teacher that we know has great content knowledge and also a good understanding of his own spatial thinking, as well as how important it is in the classroom. In this lesson, the students were primarily investigating things from a North Pole perspective above the plane. And one of the students just asked a question about what this might look like from the South Pole. So he simply said, let's figure it out together. And they all picked up the models and started looking at it from the South Pole and discussing how that might be similar or different from a North Pole perspective. And still geometric spatial visualization skills, but just from a different perspective. The other study I want to mention very briefly was more recent work looking at how students' lunar phases related vocabulary may develop as a result of instruction. We used the same assessments as the previous study, but we also interviewed 12 students who were intentionally sampled by spatial thinking ability and gender. So the 4 students from each of 3 teachers' classrooms in 2 schools were a high spatial girl, a low spatial girl, a high spatial boy, and a low spatial boy. We asked 2 questions that were basically, how does the moon phase language develop over the course of a unit, and how does this language develop in real compared to a business as usual district unit instead. So this is the unit the district used. It's shorter than the unit we use. It's also a lot more of a typical unit where instead of learning things in context through inquiry, there's a lot of stuff where students will take notes and then they'll do an activity with it. They might do a lab, then they move on to the next topic. Teachers A and B used real and teacher C used the district curriculum. So on this graph, the green portion of each bar represents the average vocabulary terms that students from that classroom used prior to instruction in their interviews. And the yellow represents the number of vocabulary terms added in post-unit interviews on average. So while they all started in different places, students from teacher A and teacher B's classrooms added a lot more vocabulary terms than students in teacher C classroom. We didn't see any trends based on gender or spatial thinking ability, but we did find that students in the project-based real classroom increased their vocabulary development more than students in the other classroom. So one of the reasons we think this is through the moon journals, where remember they were journaling and writing to learn and understand what was going on. The real unit also allowed students to use their new vocabulary immediately in context, instead of doing things like taking notes, recording vocabulary in their notebook, and then later on using it. So some final thoughts. Since we know spatial thinking is important and can be improved, we should be developing and using units like REAL that develop transferable spatial skills and vocabulary to potentially increase participation in STEM careers. Sadly, spatial ability tends not to be emphasized in schools, at least not in the United States, which not only prevents less able students from achievement in science, it also hinders us from identifying and nurturing the talents of our most spatially able students. So the way I interpret this is that if we want to address the leaky STEM pipeline, fostering the development of spatial skills may be one way to do it. And part of that, patching the leaky STEM pipeline through spatial thinking, involves working with teachers to develop their own spatial thinking and also helping them to understand the importance of spatially rich lessons for their students. Thank you.